All right, ladies and gentlemen, today we're going to be becoming familiar with parent functions and their graphs, especially with regards to technology. For your first skill, you're going to go to your graphing calculator and you're going to sketch out, paying attention to some of the important elements here that you are working through. So when I graph f of x equals x, I get a line that pretty much, if the scales were exactly the same, this would be at a 45-degree angle. And of course, as we see with a line, its biggest characteristic, or linear, is that it is a straight line, which is redundant, I understand. Next is a quadratic, and a quadratic will always have a vertex of sorts, and it's going to have a nice little curve that goes like this, like so. Something to be aware of quadratic here is a quadratic is symmetrical, which means there is an axis of symmetry such that whatever is happening over here is reflected in happening over here. So try to keep this as whatever the curve that's going on here is going to be the exact same curve going on over there. Cubic is interesting. When we get to more of the children function of this parent function, a cubic could end up looking more like this. So it looks like it has one mountain and a valley, but then it goes forever into two separate directions like this. But the parent function itself doesn't have those mountains and valleys. It simply goes something like this. It passes through here. It kind of looks like it flatlines, like flat lines there, and then comes back up like so. And that would be my parent function for cubic. Paying attention to what's important, this right here would be called a vertex because that's where things are changing. And as you can see in one of these here, is it goes up and then it starts to come back down and then up again. So there are some very interesting dips that occur on this one here. So the square root function here, it terminates or initiates here. We know that the square root of 4 is 2, so I do know it's going to get through there. And what happens is that it curves like this and eventually goes in that direction. If we were to extend it out, it would look something like this going in that. Now, it doesn't ever asymptote, so we got to watch out that it doesn't flatten out here. It keeps going up and up and up. It just slowly goes up and up and up. All right, 1 over x. So this one here is going to be curving like this, and it does asymptote against the both axes. Something like that, and that's pretty ugly. Now, we don't need to draw the asymptotes here, because they're already drawn as the axes. So in other contexts later, you're going to see it drawn, but probably as a dashed line. So later we'll do that, but here you don't need to because it's implied by the axes. This is the same situation, except something's going to be slightly different. So this one is going to be slightly more tight inside there. Also asymptote, but notice that it's not going to be able to get into the negatives of the y, and it's going to follow that general path there. So again, this is symmetrical along about the y-axis. Absolute value is fairly straightforward. Absolute value is has a vertex here, and our slopes are going to be 1 and -1, so that one's fairly straightforward to graph. It bounces there. This is would be good for like reflection of a hockey puck hitting a wall right there. There's not a lot of resistance on the ice, and so it can bounce well, as opposed to a ball bouncing on the ground, which does this sort of thing. So it's not quite absolute value. Unless you were to zoom in really close there, it might look absolute value. And exponential growth here, using, of course, the base of 2. Whatever your base is, it can change as well. So this one crosses 0, 1, and asymptotes this way, and shoots up like so. And parent functions are just the most basic form of a function. The most basic form of a function. Thank you. Most basic form of a function. And the point of the parent function, of course, is just to show you the basic shape of things. So if I have a bunch of data that happens to be looking like a V, then I could argue, and even if the V was turned upside down, again, if it was like a rooftop, I still have that idea of, oh, it's still an absolute value, it just is rotated or reflected. And the same thing goes with exponential growth or exponential decay, if it kind of looked like more like that. And the same thing, square root doesn't have to go in that direction. It could be flipped upside down and going like that if you were to transform it a little bit. The same thing here. This can describe a ball being tossed up in the air and then coming back down its height relative to time, etc. This can talk about growth of stock markets or the cost of multiple shirts, etc. All right, so each of these have a basic form. So as we're analyzing data or whatever we're doing, and we see a pattern emerge, we can associate it with one of these parent functions. And there are a gazillion different functions, so these are the basic ones that we're going to be focusing on. Once we know the basic functions that are happening, based on the nature of a parent function, we can determine a viewing window, or simply just a window, on our calculator or graphing utility, as our book loves to say, to account for special characteristics. So take a gander down here. We'll start at part C here. So here's a function that I am going to graph in a moment. Please discuss real quick with your neighbor. If this is the graph of my function on the calculator that so I punched it in my calculator and this is what I got, why is it misleading? So please go ahead and talk to your neighbor. Why is this function, the graph associated, misleading? So if we recall our square right there means that it is quadratic, and because of this negative right here, we do expect that my function's going to look, or the graph of my function is going to look like this. So it's sort of an upside down U. I've got a vertex. I'll probably cross the x-axis, probably even cross the y-axis at some point. But all I have over here is what looks like almost a straight line or a slight bend, okay? So this is very misleading because it doesn't tell me the nature of the whole thing. So because I know that this is a quadratic function, I need to keep zooming until I find out this here. So based on this function, we know a couple things. We know that it opens down because of that negative. What does this negative 20 and what does this 17 tell us? So this vertex here is going to be at 2017. 2017. Or if we were to talk about transformation, this is a reflection about the x-axis, so it flips upside down, and then it moves to the right 20 and up 17. And notice there's no coefficient here besides 1, so it doesn't get stretched at all. So I know where that vertex is at 2017. So 2017 is going to be exactly there. According to my graph, I was able to just trace a bit to see that one of mine is just a bit below 15 there, and the other one was just about 24, somewhere there. And now I can provide a sketch here of my function. Let's see what our domain and range are going to be. So B says state the domain and range of the function. Shh. Remember that the domain is just the x values that this function will correspond to, and it looks like it goes forever in this direction and forever in this direction, which means it goes forever along those this axis here, it will forever go in these directions. So in this case, my domain will be pretty much all real numbers. Now, this one here, the range is just going to correspond to this number there and everything below it. So my range is going to be y is less than or equal to 17. So we do know that this basic shape, it kind of is cool that the radical symbol is almost kind of like this sign, like if you just curved it out. That's kind of the basic shape it's going to have. Now, some of you should notice, not this negative, but what's this negative tell me about the shape? What am I going to do with the shape? It's now going to flip. It's got to do a reflection of sorts. Now, there's actually another reflection that happens here, which we're not going to tell. I mean, obviously, it's going to happen there. That's going to reflect it on the y-axis as well. So in the end, it's going to actually look like this. Okay? So you do know what its basic shape is going to look like. So when you make your when you make your window, make sure to get in the proper place. So go ahead and graph this and get a window and then sketch. So we see that we are going to be in our negatives. And my initial point here is 5, negative 9.
Also not in y. But you know,
so 5, negative 9 there, which is right here.
That's what I said. I'm trying to buy a car.
It's gonna cross right about there, drop quick, go like this, and taper out forever in that direction. Okay, so let's finish up here. What's our domain and our range? What do we expect? Notice our domain doesn't pass this mark, going that way, so domain is only this way. And of course, our range doesn't pass this one going up, so it's everything down below. So our domain is going to be x is less than or equal to 5, and our range is going to be y is less than or equal to 9. And it does go forever down. It just goes down very slowly. It goes to the left or goes on the domain much faster, but eventually it'll get to infinity in both worlds. Make a change there, negative 9 there. So on page 3, we're going to look at, so when functions are used to model real-world situations, the domain might be different. Or maybe different, and usually it's going to be a subset of the model domain. So take, for example, here. Your friend and mine, Hafiz, he makes a free throw in a basketball practice from the point of release, which is 6 feet in the air. The ball goes directly into the hoop, which is 13 feet away and 10 feet high. An equation modeling the height, bx, b of x of the ball at the in feet at time x in seconds is b of x equals negative 13x squared plus 19.5x plus 6. So number one, we're going to create a graph that would be helpful in this context. In the sketch, we're going to label the important aspects of the ball's trajectory. So, of course, important parts is where the ball starts, how high the ball can get, and, of course, when the ball hits gets into the basket. After that, considering there is nothing beforehand, and afterwards, its trajectory is now changed because of the net, etc. So after we graph, we notice that here is where Hafiz is shooting from. The trajectory goes this way. It hits the top up here, and then somewhere about here is where it hits goes into the basket. So the question here is how long, so how many seconds does it take to get there? And we want to also mark pretty much what is the highest that it does get. So that would be the vertex. So I'm going to do the trace function on my calculator to do that. So the vertex here would be about 13.3 at a certain amount of time, which is about 0.74 or 75. So if I were to sketch it here, notice that my window, there is significant amount of space from here to here, according to my window that I made, but I'm not counting by ones. I'm not counting by twos. Notice to get to here is only a second. To get to the actual, the basket right there is not quite a second. So when I do my sketch, I'm going to focus on making sure to have not count by ones, but probably count by 0.1. So marking some important points, right there is where it starts. And then at about 0.75 is where it's at the max. And then just a little bit after is at 13, something like that. So the trajectory, whoop, whoop. No neck man.
No neck.
The last point, well, just do the trace on your calculator. So when we now take this question and say, well, what is my range, what is my domain, etc., notice that I have limitations. My domain does not go back in time because this is time. So I only have to talk about domain in terms of x has got to be, in fact, there's a limit, a lower limit and an upper limit. So the lower limit is 0 because that's when the ball is in hand. And then for this context, once it hits the hoop, then essentially this is now done. It goes on to some other path. So we can estimate it to just be about 1. That'll be sufficient, or 0.9 if we trace it out 9.1. Let me go ahead and be a little more accurate there. All right, and the other one, the range. Notice here that we have, it looks like 6 feet is the highest or the lowest that it gets, and the highest it gets is about 13.3 there. So 6 less than or equal to y, which is less than or equal to 13.3, because that's its max there. All right, and the last thing, which we mentioned yesterday, is about asymptotes. And the two parent functions that we're going to look at is, as we've mentioned earlier, the inverse function and the inverse square function. And they both have x and y, the axes, as asymptotes. But asymptotes that are not one of the axes are generally marked in the graph as dashed lines. And they can be vertical or horizontal. So they're not part of the graph. Remember, when I say graph, I don't mean the graph paper. I don't mean the graph paper. I don't mean the 0, the 5. That's not the graph. That's the coordinate plane. The graph, in this context, is my red curve and my red curve. So when we actually do draw an asymptote, and in this case the axes are them, that's not part of my graph. That just tells me the limits of my graph. So when we do draw the dashed line is not my graph. It just helps explain something. So it helps me explain the characteristic of the function or the boundaries of the function or something like that. All right, so now notice this one. And we can graph it real quick with our calculator and see what where our asymptote will be. But what we see here is that the -5, and here we have to think about opposite, it is going to shift my entire function right 5. So now my vertical asymptote will be at x equals 5. So we'll have a dashed line at 5. And notice I don't need to dash along the y-axis, the x-axis, because that will also be an asymptote. And here we just make our basic function, the x, the 1 over x. And same thing here. We asymptote along that, drop down, and arrow it up there. So like we saw here, the 5 is not part of the actual graph, but what it does is describe the boundaries of the graph itself. All right, so your job, of course, is to throw some questions down do a brief summary.